Good afternoon, everyone. I welcome all of you to the most comprehensive exam preparation app, that is BYJU'S app on YouTube channel. I welcome everyone for the GATE AIMERS 2022. Today's topic is Shallow Foundation. All of you please join. Hello Chetu. Good afternoon. I hope all of you are preparing well and staying safe. Yes. So let us start now. Let us start now our topic. All of you please do not forget to share and like. Please share it and like it. Do not forget to like the session. Now, this is my small introduction. As you know, hello Aman. And on 15th November, that is day after tomorrow, I will be taking class for deep foundation, that is from the soil mechanics. A little bit mistake here. This is from soil mechanics. It will be your deep foundation. Then after that, Ankit sir will be taking class for construction material management, and or these topics will be conducted on 16th, 18th and 20th November, and it will be continued. Hello Chandrasekhar. No need to get depressed. See, now we will discuss about shallow foundation, and on 15th I will discuss about deep foundation, and you will get confidence, right? So now Telegram, this is my Telegram channel. Anyone can join there by just typing civil by Md Ansari Sir. You can find the channel and you can join me. These are the staff faculty of BYJU'S Prep for the civil department, and these are the courses running on, that is for Vision GATE 2022 and rank up, and Vision 2023 is going to run, which is very helpful for the candidates who are aspiring for 2023 GATE. Now today what we will see, the basic of all bearing capacity, basic definitions, Tajikis Assumption, its bearing capacity for different shape, and then failure of soil beneath the foundation, groundwater table also we'll see, then Skempton's NC value I'll let you know, and based on that we'll solve the numerical. That's all. Let us start with the session. So first thing is that already you have a different type of shallow foundation, right? Like strip foundation, isolated foundation, combined footing, raft foundation and strap foundation, right? So out of that strip foundation, we are saying that when the length is far greater than your width of the foundation, you can say that the wall foundation generally which we used to provide in early days, isn't it? So the strip foundation is when the length will become very much large compared to the width. Suppose this is your footing, and the length of footing will become, if the length of footing is too much large, greater than width of footing, then we are calling it as a strip footing. Then isolated footing, already you know that individual footing you can construct, maybe the isolated way, maybe it will be of your step footing or the trapezoidal shape footing, whatever you have. Then you have, that is independent, one footing will be connected with the one column. Then we have a combined footing, when we are combining the two column together, when we are combining, then we are calling it as combined footing. This generally we used to provide on the boundaries of our area, right? When we don't have much space, then we are providing it, this type of footing. So a common base will be there, and for the common base two column will be sharing. Then you have a raft foundation, when the soil is little bit, soil doesn't have a good bearing capacity, or maybe the settlement is more and all, if there is a chances of differential settlement. So to reduce that differential settlement chances and to reduce the settlement also, raft foundation we are using, where a complete area will be covered with the footing and column will be established over it. That's all. That we are calling it as a raft footing. Then strap footing is nothing but when the two column we are joining with one beam at the footing side, right? The two columns, the two footing actually you are joining with one beam, that we are calling it as strap footing. So these are the different type of footing we have. Now when the depth by width ratio is less than 1, then we are calling it as a type of foundation is shallow foundation. When depth of foundation and width of foundation, the ratio of these two are less than 1, then we are calling it as a type of shallow foundation. Now let us go for some basic terminologies, that is nothing but gross pressure. Gross pressure is means what? If you have a footing, over the footing load will be coming from the structure, isn't it? The structural load is going to come. Then along with that you have a soil which is filled at this place. So total load including the surcharge, this soil which we are filling it after excavation. First we will do the excavation, then we will cast the footing, then after that whole load is going to come over that footing. So the surcharge and the whatever the load is going to come, the total load we are going to recognize for this gross pressure. Then next one is your net pressure. If you remove that surcharge of the soil load, that is gamma d. If suppose gross pressure I am saying that is some Qg, and if I will remove the gamma d, I will say that it is now nothing but my net pressure which is occurring at the base of the footing. Then we have ultimate bearing capacity. This is nothing but the capacity of soil to take the load. Means one thing you should understand, soil actually only gets fail in the shear, right? Now if you just keep the footing here, if you apply the load over to the footing, what will happen? At some point of time the soil beneath the footing is going to get failed, and the failure of course is due to the shear failure. Now that failure, just the load at which the shear failure will occur beneath the footing, that load we are calling it as ultimate bearing capacity. It is related to once again your gross pressure. Then from the ultimate bearing capacity, if you will remove the surcharge load, that is gamma d, that bearing capacity we are calling it as net bearing capacity. Net bearing capacity or net ultimate bearing capacity, which is nothing but ultimate minus gamma d. So ultimate bearing capacity is the maximum load which can be taken by the soil, that's all, before the failure. The maximum load which can be taken by the soil before the failure. Now next one is your net safe bearing capacity. Once you have calculated its net ultimate bearing capacity, the net safe bearing capacity will be net ultimate by some factor of safety if you are keeping for the foundation or footing. Then safe bearing capacity, if you want to calculate the safe bearing capacity, will become simply net safe plus gamma d. So this is the basic terminology and some of the features you should remember. Next one is the type of failure beneath the footing. So it has been categorized in three aspects, right? In three different category we have categorized it. That is, first is your general shear failure. Suppose you have a footing here. This is our footing and this is the surface. This is the ground surface. Now after load provided, the failure actually is, we are saying that in general shear failure, the failure plane actually reaches till the ground surface and the bulging of soil will occur. That is the feature you are observing. See, if you have a footing beneath the ground, suppose now once again I'll draw the so beneath the ground, if you have a footing, what kind of failure you will be observing? That failure of your footing has been categorized in three different part. One is your general shear failure. General shear failure means you will observe the bulging of the soil above the ground. Why? Because the failure plane is actually reaching till ground, and the whole soil is taking part in the failure. At the same time, the tilting of your footing is also occurred. Tilting of footing will be observed. So tilting means, although I am showing it very too much, it is exaggerated diagram, you can understand, but the tilting of the footing also will be observed during the time of general shear failure. So this type of failure generally it is occurring when you draw the curve between the load versus settlement. This is the curve you will be observing here. Acha, from this particular curve you can remember one thing. For the general shear failure, you see that if you remember whatever you have studied in the strength of material, though it is not related to that, but if you can connect it, see, when you used to apply the load in a tensile testing machine, what is going to happen? At some point of time, it is going to get failed, isn't it? There is upper limit and lower yield limit. So the failure there is due to the carbon slippage and all. But here actually you can imagine when the load is applied here, there is a shear failure. See, shear strength of the soil is due to interlocking cohesion and friction, isn't it? Why this kind of observation we have achieved? This is, you know, very clear cut. It is indicating what must be the ultimate load at which this, you know, failure will start. This ultimate bearing capacity is very much quite visible for the general shear failure. It is quite defined. Why? Because you can imagine if it is a very dense soil, there will be some interlocking and all. If you apply the load, once the interlocking will get failed, the load once again will reduce. So that is why in a general shear failure, we are generally used to say that it is happening for the dense soil. It is happening generally for the dense soil like a dense sand and all. Are you able to understand that? That is what your general shear failure. So few of the points you can remember for general shear failure. The failure surface is reaching to the ground surface, right? Then it is bulging of the soil will be considerable bulging of the soil you can observe over the ground. This is your ground surface. Over the ground there will be bulging of the soil, right? Then tilting of footing, as I told you, and the failure is a sudden failure. The failure will happen, it is a sudden failure. So it is, we are calling it as on a dense soil, or we are saying that it is a kind of brittle failure, right? And ultimate bearing capacity is well defined. Now imagine about the another type of failure, which is we are calling it as local shear failure. Here bulging is almost negligible. It is quite difficult to observe any kind of bulging of soil. Why? Because the failure plane is not reaching till the ground surface. If the failure plane is not reaching, you can imagine that if the whole soil is not participating in the failure, only if the beneath the foundation, if some of the soil is going to get failed, if these, you know, all the soil are not participated in the failure, then it is quite not easy to observe any type of tilting. So tilting and bulging you cannot observe for the local. It will be very minimum. Are you able to understand that? So in a local shear failure, the tilting and bulging will be very minimum and you cannot observe it, because the failure plane is not reaching till the ground surface as it was there in the general shear failure, right? And punching shear failure is quite interesting, where if the soil is very soft and all, what will happen? Simply a large settlement will be observed instead of tilting or bulging. A large settlement will be observed in your punching shear failure, right? Now if you draw the curve between load versus settlement, same way what you can observe, it is better you draw all the three curves together. This was, I just told you, it is a general shear failure. Then if you draw the curve for local shear failure, of course a clear cut ultimate bearing capacity will not be observed. Then if you draw it for the punching shear failure, you can observe that after some of the loading, now you have a large settlement. You can compare the curve between general to local to punching shear failure. In a punching shear failure, if you draw the curve between load versus settlement curve, the settlement is very huge for the punching shear failure, right? These are just the common on few important points. Now come to the Tajikis assumption. Acha, before Tajiki, you know that Tajiki has adopted the, you know, analysis conducted by the Prandtl. Now Prandtl actually assumed that beneath the foundation, the surface of the foundation was smooth, right? The surface of the foundation was smooth, and at the same time he has taken that concept from the punching of the metal, right? Now Tajiki did the analysis and he said that I will consider the base of the footing as a rough, and one of the, you know, some of the soil mass which will get stick to the beneath the footing, I will be considering it as a elastic equilibrium, right? So the soil which is beneath the footing, we are going to consider it as a one piece, your footing and beneath the footing whatever the soil you have. So few of the assumptions if you see in the Tajikis analysis, then what he got the formula for bearing capacity, that is quite important, right? Now for a footing, he conducted that analysis based on strip footing, that is when the length of the footing is quite larger than the width of the footing. Soil is homogeneous, base of the footing is rough, as I told you. General shear failure actually he assumed, although he has assumed the general shear failure, but when he gave the analysis, when he gave the formula, when he just derived the formula for bearing capacity of the soil, what must be the bearing capacity of the soil, then he actually assumed the failure plane was not reaching till the surface of the ground, till only base of the footing he has he considered the failure plane, right? So understand this point very clearly. General shear failure he has assumed, but the failure of the plane he has not taken till the surface of the ground. That is very important point. Then loading is vertical and symmetric, and sharing a distance between the soil and ground surface. So that's what he's saying, that all the soil which is here as a surcharge is not participating in the failure, isn't it? If I'm saying that if the failure plane is not reaching till the ground surface, what is the meaning? If the failure plane is reaching till the ground surface, means the whole soil here is participating in the failure. Now if it is not reaching here, then it means I'm ignoring the soil above the footing for the participation of failure. That is what he did. Now these are the few assumptions. If you understand, it will be very helpful for all of you. Now if you have any doubt, please tell me. And shear strength of the soil has been governed by Moore-Coulomb criteria. Let us now talk about some of the bearing capacity for different shape of the footing, which has been analyzed and which has been calculated by Tajiki. So for the strip footing actually and the general shear failure, he found a bearing capacity of the soil can be calculated based on the three coefficient he gave, that is NC, NQ and N gamma value. Based on that, you can calculate the bearing capacity of the soil, where C is the cohesion of the soil. Gamma, here three terminologies are there. This is the second terminology and this is the third one. Gamma present in the second one is beneath the footing, the soil which is beneath the footing. This is the gamma for second term, and the gamma here, the surcharge of the gamma is for the third term, right? This is what? Oh, sorry. This is your second one. This is your second one, and this is for your third one, right? Now bearing capacity of soil you can calculate with the help of Tajikis. Now this is the only equation, if you remember, you will be getting, it will become very easy for you for shallow foundation as well as for pile foundation, because this is the only formula we are utilizing throughout our shallow foundation and pile foundation with some modification and all. So if you want to give a good start, if you want to get a hold in your footing, foundation and deep foundation, then you should be very thoroughly, you should understand this formula. You should remember this formula, each and every terminology here. Now this is actually, he did it for the strip footing. As I told you, for the general shear failure he conducted the analysis. Now for the square footing, if you will just calculate, only you need to multiply the coefficient by 1.3 here and 0.8 here. If you multiply, it will become 0.4. If you go for the rectangular footing, that is the shape factor we are multiplying. This for the rectangular footing, if you can multiply with 1 plus 0.3 b by L. Acha, you can remember it also. See, if you want to make this rectangle as a square, this b and L will become same. If b is equal to L, it will become 1.3. And if this is 0.4, right, this is 0.8. Now you can see that 0.8, this 1 minus 0.2 into b by L. If your b is equals to L, then 1 minus 0.2 will also become 0.8. So you can just verify if you have remembered the formula for square footing. For a circular footing, just you multiply, first coefficient is same, that is 1.3, and the last coefficient is your 0.6, right? Now you understand few of the things here. It means that bearing capacity, if you want to determine for a footing, it is depending on the cohesion of the soil. It is depending on the NQ and N gamma value, which is depending on the phi, that is shear angle of the soil, isn't it? That phi. So angle of friction is also very important criteria. So C and phi. So all the bearing capacity, whatever you are calculating, along with that C and phi, along with that, it is also depending on the depth of the footing. What is the meaning of that? It means if you are going at a larger depth, the bearing capacity of the soil will be high, isn't it? If you are coming at shallow depth, your bearing capacity of the soil will be low. At the same time, you can see that the width of footing is also a criteria, although you know that it is not the total load carrying capacity I'm talking about. Please do not misconduct it. So load carrying capacity is different and bearing capacity is different. Bearing capacity is nothing but the pressure. It is nothing but Newton per mm square. The bearing capacity of the soil. Now, if you are increasing the width of the footing, then your bearing capacity of the soil also increases. So understand very clearly, it is depending on C, it is depending on your phi. That phi is actually indirectly for NQ and N gamma. Then it is depending on your depth of the footing and on your width of the footing, right? But this formula has been given by Tarjagi for the general shear failure. If you want to calculate it for the local shear failure, then you have to make few changes. That is, C value will become 2/3 of C, and tan phi you can take that 2/3 of tan phi, then only for the local shear failure. That's all. Acha, along with that, few more things you have to consider here. Suppose you have a cohesive soil, that is very special case. You must remember it always. Especially for the cohesive soil, your NC value will be taken as 5.7, your NQ value will be taken as 1, and your N gamma value will be taken as 0. This is only for the purely cohesive soil, right? Now you tell me, if it is a pure cohesive soil, the ultimate bearing capacity for the strip footing, if I'll write it down, this QU will become, what will become the QU value? The ultimate bearing capacity of your soil will become CNC plus gamma D. Now actually I can ask you whether it is depending on width of the footing or not. Of course it is not depending on the width of the footing. So if you have a purely cohesive soil, the bearing capacity of the soil is not at all depending on your width of the footing. But once again I will tell you, do not misconduct it with the total load carrying capacity. Of course it is the pressure at which the soil will get failed. This is the maximum pressure which can be handled by the soil. The bearing capacity is nothing but your maximum pressure which can be handled by the soil before failure. Now if you want to calculate the total load carrying capacity, of course the pressure multiplied by whatever the area of footing you have, isn't it? Now if I'll ask you what is the net ultimate bearing capacity, so net ultimate, as I told you, will become QU minus gamma D. Now if you QU minus gamma D, if you will do, what you will get, that is nothing but it will become CNC, and from this you can understand the net ultimate bearing capacity of the soil is not at all depending on either depth of the footing or width of the footing. So at whatever depth you want to construct your footing, it does not matter. The bearing capacity, that net ultimate bearing capacity, will remain same as it is. Did you get that? So these two are also very important feature here. Now let us see about the groundwater table correction. So if you have a footing with some depth, and this B is actually the width of the footing, this B is nothing but width of the footing. So till from base of the footing till your whatever you have a depth, till that whatever you have a width of the footing, till that it is considerable. Beyond that, whatever is happening, we are just ignoring it, right? That is also if you go through that particular chapter, what is that, soil exploration and all, you will understand that isobar, when you are preparing for any of the load beneath the footing, beneath some of the foundation, if you have a width of the footing is B, beneath width of the footing you just consider B. Beyond that, maybe less than 10% of the stress is going to come. That is why we are actually ignoring it. Are you getting my point? If you go to the vertical stress, if you draw the isobar, you know that isobar, if you are just searching for the points which has the same pressure, the points of the same pressure due to the applied load. So at some particular depth you are getting it, but after 10% variation it is not considerable, and hence we are ignoring it, right? So based on that, just we have considered that, okay, let us see that whatever the width you have, till that particular depth we will consider. After that we are not going to consider anything. Now if this is the footing you have, and this is the formula, suppose for the strip footing, to calculate the ultimate bearing capacity. Now suppose you have a groundwater table at the surface, means the groundwater is reaching at your surface, then what will happen? It is completely saturated, isn't it? The groundwater table, if it is reaching at your surface, it is completely saturated. Now the gamma value, simply instead of gamma you will be conducting your gamma dash. That's all. Instead of the gamma, see, already gamma submerged you will be using it for both of them. But instead, suppose if the groundwater table is in between somewhere, instead of at this place, now the groundwater table is here. What will happen now? If the groundwater table is at this location, then how you will calculate the bearing capacity of the soil? Suppose this depth is Z, and this depth will become now B minus Z, because this is the depth we are going to consider. So if the water table is at depth of Z from the base of the footing, right? if it is at depth of the jet from the base of the footing, how you will consider for the gamma. Now, the bearing capacity of the soil, if you want to calculate for the strip footing, once again, it will be CNC gamma D NQ. Now, there is no need to worry about, because water table is here. So, whatever the soil you have in the surcharge zone, here you don't have a water table, so you don't have to worry at all. Simply gamma D NQ, whatever you have written, it will be same. Plus, now you only need to correct the gamma for this particular area. So gamma whatever available for this particular area before, above the groundwater table, whatever gamma you have, suppose gamma T, some gamma T you have, that gamma T into that Z plus this gamma submerged into B minus Z. That is how you are accommodating for the gamma. That's all. You are calculating the value of gamma for the water table correction. Did you get that? Now, if the water table will be, instead of water table here, if the water table is at this location, if water table is here at some depth h from the surface of the footing, from the surface of the ground, so this depth will become d minus h. Instead of correcting the gamma value at the last one, you will be correcting it here. That's all. See, this correction, instead of doing there, you are doing it here, and it will remain same. Gamma here will become gamma submerged. This is the one way of correction. Generally, we are doing it for the calculation of bearing capacity, right? At the same time, we used to calculate things with the help of CNC plus, instead of that, RW1 gamma DF NQ and plus 0.5 RW2, that is the water correction factor, right? Sometimes we are using the water correction factor, that is RW1 and RW2. How we are using it, I'll just show you. Water correction factor, that RW1 and RW2, it is almost same type of formula. Suppose if I'll consider RW1, that is for the, or maybe if I'll consider RW2. Suppose if I'm writing down RW2, what I will write it down? It is nothing but 0.5, 1 plus if it is Z, it will be Z by total width, total depth, that is B. Similarly, it is similar to that same RW2. I can write it down RW1 also. Sometimes if directly they are asking what must be the water correction factor one should apply for calculation of bearing capacity, then you can use this formula. So 0.5 and same formula you can use, that is H by DF. That's all. So this is how we are going to calculate our bearing capacity if the groundwater table is varying from one position to another position. Are you able to understand that? Then after groundwater table correction, if you see, this is one of the important thing. See, actually after conduction of Tajikis analysis, Maha did the analysis, and Maha, remember that whatever I told you regarding your failure plane, as the Tajikis in Tajikis analysis, the failure plane he has considered till the base of the footing. Maha only conducted the analysis where he has considered the failure plane till the ground surface. After that, Skempton also came, and Skempton did the analysis only for the cohesive soil. He did the analysis only for cohesive soil, and he found the NC value, different NC value formula. That's all. For the strip footing, for the circular and square footing, and for the rectangular footing. Now remember few things only here. Generally, if you go for the deep foundation, that is for pile foundation, you are using that NC value. If you remember the, when you are calculating the load carrying capacity, the formula you are using is 9C. Do you remember that in your deep foundation? That 9 value you are using it from here, Skempton's value, right? See, what he is saying, that if I'll consider only the square or circular footing, if you have a square or circular footing, if the depth of foundation by width of foundation is larger than 2.5, he is restricting the value to NC 9, means total maximum value will become 9, not more than 9. So if depth of footing by width of footing is less than 2.5, you keep the values and you get the value, right? So minimum will be that depth of footing is 0. So minimum value for a circular or square footing for an NC value will become 6, that is df by b will become 0, and the maximum value will become 9. Remember that. right? When the df by value will df by b will become 2.5. now that maximum you are using for the deep foundation. Why? Because df by b is larger than 2.5 in your pile foundation, isn't it? That is why every time when you are calculating, you are using the 9c value. Now let us solve few of the problems from here. That is, can you just read it out? Rankine in his bearing capacity ignores the cohesion intercept. The first option is that as a Rankine theory, bearing capacity is 0 if the footing is kept on the surface. For deriving the bearing capacity of the soil beneath the footing has been considered under plastic equilibrium, then minimum depth of the foundation can be calculated as per Rankine's theory. It is the whole all the statement I have provided as per Rankine's theory. This question actually I just prepared only so that you can remember these points for the Rankine's theory. So as per Rankine's theory, yes, all the points here are correct. He did the analysis for the cohesionless soil, hence he ignored the cohesion intercept. That's correct one. And minimum depth of the foundation you are calculating with this formula only. So all the points are correct here, if you remember. Then the analysis done by Prandtl also, as I told you, few of the points generally we are missing it. Sometimes it used to come. In fact, once I have seen that it was there in the GATE examination also. So Prandtl's theory for the bearing capacity extended from the penetration of punches in the metal, which I told you. Then Prandtl assumed a smooth base of the footing. This is also correct. Prandtl uses the theory of plasticity for defining the bearing capacity of the soil. That is also correct. And when he did the analysis, he found the bearing capacity by pi plus 2 into Cu, right? Cohesion for undrained condition. All the options are correct here. Then the another one, if you'll see, which of the following statement is not correct for the bearing capacity of the shallow foundation? Ultimate bearing capacity is well defined for the general shear failure. This is actually correct. I told you for the load versus settlement curve, if you draw load versus settlement curve, the ultimate bearing capacity, especially for the general shear failure, is well defined. So this is correct one. He is asking which one is not correct here. Meyerhoff has considered the failure plane till ground level. That is also correct. Just now I told you. Skempton did the analysis for the cohesive soil. This is also correct. And tilting and large settlement can be observed in local shear failure. This is incorrect. As I told you, the tilting and the large settlement. See, the large settlement will be observed only for the punching shear failure, and tilting will be observed for the general shear failure. We are not observing anything for for local shear. A very small amount of tilting or a very small amount of bulging of soil will be occurred for the local shear failure. That's all. Are you able to understand that? Then, as per Skempton's NC value for circular pile varies between, just now I told you, if you'll consider that formula which I gave it to you, from there the Skempton's value varies from 6 to 9. For a circular or a square, or for a circular and a square, the Skempton values varies from 6 to 9. Minimum it will be 6 and the maximum will be 9. Whatever depth you consider, you are not going to beyond, you are not going to take the value beyond 9. The ratio of net ultimate bearing capacity of strip footing to square footing resting at a depth of 2 meter on a cohesive soil is given. Now what will be the ratio of net ultimate bearing capacity of the strip footing to square footing? You should know that what is net ultimate bearing capacity. See, it is on a cohesive soil, the net ultimate, isn't it? So you know ultimate bearing capacity already. So whenever you are doing this type of problem, I will just request you, every time you write down the complete formula for a strip footing given by Tajikis, that is CNC plus gamma dNq plus 0.5 gamma bn gamma. Do not forget that formula. Remember every time and write it down. Now he is asking for the net ultimate, that also for the strip by square. So for the strip footing it will be CNC plus gamma dNq, isn't it? For the cohesive soil, first of all for the cohesive soil, if it is for the cohesive soil, your n gamma will become 0, nq will become 1, and you will get CNC plus gamma d, and net ultimate if you will calculate, you will get CNC. That's all for the strip footing. Now similarly, net ultimate, this is for strip footing. If you are calculating it for square footing, the net ultimate will become simply 1.3 CNC. That's all. Now he's asking what is the ratio between these two. The ratio will become 0.77, that's all. Strip by 1 by 1.3, isn't it? The ratio of ultimate bearing capacity. So this is all. Hello Tushar, it is almost a kind of revision for your shallow foundation. In this shallow foundation, just you have to add a plate load test, that's all. You add a plate load test and it is a kind of complete revision for you. The net ultimate bearing capacity of soil is 25 ton per meter square and the density 1.7 ton per meter cube. The safe bearing capacity at 1 meter below ground surface taking factor of safety 2.5 will be. He is asking about what is the safe bearing capacity. The safe bearing capacity can be calculated. How you will calculate? First of all, you see the net ultimate bearing capacity is given, that is QNU is given to you 25 ton per meter square. Right, from the net bearing capacity, net ultimate bearing capacity, you can calculate the net safe bearing capacity, which is 25 by factor of safety 2.5. You will get 10 ton per meter square. Then from net safe, you can calculate the safe bearing capacity, which is nothing but QNU. QN is that net safe plus gamma D. Gamma is given as 1.7 and D is also given as 1, and it will become 11.7. Right. For a square footing resting on a clay at a ground surface, the ultimate bearing capacity as per Tajikis theory is, if you are keeping your footing just over the surface, if you are going to keep the footing over the surface, if you are keeping the footing just over the surface, as per the Tajikis theory, the ultimate bearing capacity is what? CNC plus gamma D n cube plus 0.5 gamma B n gamma. Now gamma B n gamma. D, if it has become 0, the ultimate bearing capacity is CNC plus 0.5 gamma B n gamma. And also he is asking for clay. Clay is a cohesive soil, so n gamma also will become 0. So QU is going to become a CNC. This is not net ultimate. This is your ultimate bearing capacity, which is now CNC. So he is asking what is the value now? Square footing. Okay, just I missed one more point, that is the square footing. So for a square footing, you know that a shape factor we are going to use it for the square footing. It is 1.3 here. The ultimate bearing capacity will become 1.3 and ultimate bearing capacity will become 1.3. And NC value for the cohesive soil, already you know that it is 5.7. So 5.7 multiplied by 1.3, of course this is the only option you have available. Right, that's all for today. You go and revise it completely. Thank you everyone, and we will meet once again on 15th, and I'll revise complete pile foundation on that day. So do not miss that particular session. We'll meet on 15th of November at 3 p.m. for a complete pile foundation, and tomorrow I'm going to tell you about how one can do the strategy and planning for last 75 days. What must be the strategy and plan for GATE 2022 for last 75 days. So do not miss the session tomorrow as well. Thank you everyone. Have a nice day.